So now that we have defined paths, we can define a very important concept for graphs, which is connectedness. So a graph is connected if there's a path between any two vertices. And again, we're speaking about undirected graphs. We will come back to directed graphs in a bit. So it's connected if there's a path between any two vertices. It is disconnected otherwise. So for example, a graph like this one, for example, this is connected because there is a path between any two vertices. Just to give an example, this vertex and this vertex, there is a path from here to here. There you go. And you can pretty easily see that if you choose any two vertices in this graph, you can find a path between them. So it is connected. On the other hand, something like this graph is disconnected because, for example, there is no path between these vertices A and B. For example, starting from A, the only place you can get is these other two vertices. You cannot get to B by any sequence of edges. So this graph is disconnected. So essentially, a connected graph is easy to recognize visually because it's in one piece, unless you're you're drawing the pieces over each other like this, which maybe can make it a little more confusing. But you can see that a disconnected graph is basically just a couple of different graphs sat next to each other. So there is some terminology for this as well. A connected component of a graph is a maximal connected subgraph. So in this example, there is one connected component, which is the whole graph because it is connected. Whereas in this example, there are two connected components, namely each of the little triangles. So this one and this one. So connected components are basically the technical term for the fact that a disconnected graph is just a couple different graphs sat next to each other. And just as a quick, a quick connection between the two things, you will notice that a graph is connected. I can even write this down. Graph is connected exactly when it has one connected component. If you have more than one connected component, then you are disconnected. So just to give another example, and to connect this to something we talked about before, the connected components of a graph will often have some kind of meaning if your graphs are being used to represent something. So connected components might use this abbreviation for components. Often have meaning, essentially just because paths through graphs often have a meaning to them. So for example, recall a finite partially ordered set, finite coset, can be diagrammed as a Hasse diagram, which is essentially a graph. So it's a graph, maybe with some extra information. Maybe you could call it a directed graph if you wanted to keep track of the directions of the edges. But you can think about it either way, depending on what you're interested in. But if we think about it in this sense, as an undirected graph, and we think about the connected components, what do they mean? So two elements are in the same connected component. If and only if they are comparable. So remember that comparable means that either x is less than or equal to y, or y is less than or equal to x. And being comparable, or being connected in the Hasse diagram, means that there's a sequence that x is less than or equal to the next thing, and the next thing, and the next thing is less than or equal to y. And that is exactly what it means to be comparable. So in this example, when you are diagramming a coset as a Hasse diagram, the connected components encode exactly which groups of elements are comparable.